Installation of online instrumentation, a tutorial, integrated design philosophy for operational accuracy and maintenance access. System overview and design intent. Installation of online instruments must be strategically tailored to ensure accurate process measurements under all expected normal and abnormal operating conditions. Optimal instrument hookup configurations are to be selected based on measurement integrity, lifecycle cost, and ease of maintenance. Heating, insulation, sealing, and purging techniques must be judiciously applied only when alternative hookup strategies offer less attractive trade-offs in terms of total cost of ownership, TCOO, operational accuracy, or maintenance complexity. Remote versus direct mounting, configuration principles. Two principal design philosophies are employed: remote mounting and direct mounting. Remote mounting relies on a modular platform allowing for optimal access, integration of heating elements, in situ calibration, and reliable impulse line routing. Conversely, direct mounting reduces component count by integrating instrument, manifold, and isolation valve into a compact assembly mounted directly onto the process connection. While direct mounting reduces installation labor and costs, it introduces greater stress and thermal exposure to the instrumentation. Material and component specifications for integrity under process stress. All wetted impulse line components should be fabricated from AISI 316 stainless steel, rated to at least 413 bar G from -200 degrees to +38 degrees Celsius, with alternative alloys, e.g. Incolloy, Monel, used in aggressive or high-temperature services. Proper installation of compression fittings, consistent make type usage, and rigorous adherence to manufacturer's torque procedures are mandatory to prevent leakage and failure. Tubing and fittings must be pressure tested upon installation to validate joint reliability under actual process pressures. Instrumentation and support engineering. Instrumentation must be mounted on dedicated supports that account for thermal movement, process vibration, and insulation compatibility. For remote-mounted devices, impulse lines should be short, sloped 1/5, and free of stagnant pockets. Supports should prevent galvanic corrosion and avoid mounting on grating or insulated pipe unless specially approved. Direct-mounted devices must account for process nozzle stress limits, ensure electronics are shielded from extreme temperature, and consider misalignment risks during dual-tapping installation. Connection integrity and leak prevention strategy. Process connection design must prioritize isolation and containment. Dedicated primary isolation valves are mandatory, with optional shared isolation in specific loop configurations. Gauge blocks, flanged adapters, and compression fittings must be selected to minimize connection count while maximizing integrity. Top-mounted tapping on horizontal lines is standard to avoid sediment blockage. Side or downward tappings require seal pots and venting provisions to prevent measurement drift due to gas entrapment. Impulse line engineering for precision and resilience. Impulse line arrangements must factor in flow dynamics, mechanical stress, and environmental exposure. Short, downward sloping lines are preferred, with regular support intervals and separation from metal contact points using spacers. Differential pressure instruments must use standardized connections, IEC 615 and 18, or approved proprietary variants, with mounting designed to absorb thermal expansion and vibration forces. Flushing, filling, and safe disconnection practices. Where process fluid poses environmental or safety hazards, impulse lines must be equipped with capped non-return flush connections to facilitate seal liquid replacement, chemical neutralization, or decontamination. Drain and vent lines must include anti-tamper measures and directional tubing to guide effluent safely. Compatibility of heating and insulation with instrument integrity. Heated instrumentation, particularly in low temperature or wax-prone services, requires robust insulation, effective heat tracing, steam or electrical, and removable enclosures for maintenance. Temperature ratings of all tracing elements must be confirmed against process upper design limits. Electrical tracing must comply with hazardous area classification and provide fail-safe operation. Special application adaptations and diagnostic safeguards. Steam services necessitate condensate seal pots. High pour point or hydrate risk fluids require heating, purging, or diaphragm seals. Suspended solids, toxic fluids, and waxy residues demand tailored approaches such as sloped installations, remote seals, and external purge mechanisms. Low-range gas services must mitigate slug formation using wide-bore tubing or immediate proximity installations. Calibration, span adjustment, and density compensation. For accurate zero and span calibration, wet leg systems must be designed with appropriate seal liquids, equalization lines, and manifold arrangements. Seal liquid selection must account for evaporation, viscosity, compatibility, and density consistency. Systems must permit in situ calibration under pressurized conditions, with specific accommodations for intelligent or non-intelligent devices. Purge and self-cleaning mechanisms for plug-free operation. External purging, though maintenance intensive, is justified only when self-purging or other design solutions fail. Purge gas or liquid systems must use constant flow regulators, check valves, and tracer blocks, ensuring minimal impact on measurement accuracy. Self-purging configurations demand strategic placement of insulation, exposed tubing, or heating depending on process volatility. Conclusion: diagnostic integration and plant lifecycle readiness. All installations must be traceable, reproducible, and diagnostic capable. Whether direct or remote mounted, the system must facilitate lifecycle management, including in situ testing, purge assurance, and density drift compensation. Every design decision must reflect the overarching priorities of measurement precision, personnel safety, maintenance accessibility, and robust compliance with industry best practices. Instrument process connections, foundation for accurate measurement and safe maintenance. Precision access and isolation control. Online instrumentation must incorporate robust, dedicated primary isolation valves to enable safe removal, calibration, or maintenance without interrupting the process. These valves act as the first barrier of protection and must be rated for full process pressure and fluid characteristics. Where instrumentation is deployed in parallel to extend range coverage, shared isolation may be employed only when each instrument has its own independent secondary isolation. This ensures operational safety and containment even during partial loop servicing. For applications prone to plugging, such as slurries or waxy fluids, straight-through isolation valves, such as gate, ball, or plug types, are preferred to enable direct rotting and mechanical clearing of blockages from process connections. Leak prevention and connection quality. The integrity of instrument process connections is critical for system accuracy and long-term reliability. Flanged surfaces for gauge blocks and adapters must conform to ASME B16.5 standards to ensure proper sealing. The design must minimize the number of joints, prioritizing flanged or compression-type connections over threaded ones to reduce leak paths. When threaded connections are necessary, parallel threads with soft annealed metal sealing rings are preferred over tapered threads like NPT, which require additional sealing agents such as PTFE tape. This enhances long-term tightness and simplifies dismantling during maintenance. Optimize tapping locations for clean signal recovery. On horizontal lines, instruments should typically be connected at the top, either vertically up or at an upward angle to minimize accumulation of solids or debris. However, for liquid services, this orientation can cause gas entrapment. In such cases, side tappings are preferred. If top tappings are unavoidable, seal pots and minimal elevation differences must be used to manage potential gas pocket formation. In fluids containing vapors or dissolved gases, vertical process connections are preferred. Where only horizontal lines are available, tapping should be done from the side or at a downward angle to ensure gas rises back into the process, and the impulse lines should slope down toward the instrument to promote auto-venting. Downward tappings, due to their fouling risk, require explicit approval. Conclusion: designed for containment, access, and reliability. The design of instrument process connections must support precise measurement, safe access, and leak-free service under all process conditions. Every connection, whether isolated, flanged, or threaded, must be configured with consideration for fluid dynamics, solids carryover, and operational safety. Proper tapping orientation, high-quality sealing practices, and mechanical clearances are all essential to maintaining long-term measurement reliability and minimizing maintenance risk. Remote and direct mounting connections, engineering for modular integration and compact efficiency. Remote mounting, modular precision and separation of responsibilities. In remote mounting configurations, instrument process connections must terminate in a standardized lap joint interface to enable seamless integration with the tubing and manifold system. The preferred termination is a DN15 lap joint flange coupled with a lap joint tube adapter. This setup ensures mechanical robustness and standardization across diverse installations. The primary isolation valve, lap joint flange, gasket, bolts, and any associated heating or insulation elements fall under the domain of mechanical engineering. Instrument engineering takes over from the lap joint tube adapter onward. This clear demarcation supports efficient scope allocation and simplifies construction and commissioning workflows. The lap joint configuration enables rapid connection of impulse lines via compression fittings, while maintaining alignment and minimizing stress on process nozzles. This design also facilitates pressure testing and field validation by providing a secure, standardized mechanical interface. Direct mounting, compact design with integrated functionality. In direct mounting applications, the instrument is affixed directly to the process connection, often using a flanged gauge block or integrated manifold block. For pressure gauges, flanged gauge blocks offer structural support and standardized alignment while preserving measurement fidelity. More advanced configurations consolidate the primary isolation valve and instrument manifold into a single compact housing, commonly referred to as a monoflange. These integrated components reduce leak paths, minimize installation time, and simplify overall footprint. Their application requires joint coordination between mechanical and instrument disciplines to ensure that mechanical integrity and measurement accuracy are preserved under varying thermal and flow conditions. Such designs are particularly suited for clean fluids and compact layouts where access is limited, but they must be vetted for compatibility with pipe stress, nozzle loads, and vibration tolerance. The selection of monoflange or integrated blocks must consider the trade-off between accessibility, maintainability, and long-term measurement reliability. Conclusion: interface-driven configurations aligned with performance goals. Whether employing remote modular systems or compact direct mounting solutions, instrument process connections must align with performance targets, operational constraints, and lifecycle support strategies. Remote mounting excels in environments requiring access, flexibility, and separation of functions, while direct mounting offers compactness, reduced component count, and improved dynamic response. Selection must be tailored not only to process parameters, but to construction sequencing, diagnostic capabilities, and plant standardization strategies. Mounting remote instruments, structural integrity, and accessibility in harsh conditions. Instrument mounting supports engineered stability with environmental compatibility. Remote mounted instruments require robust, dedicated supports to ensure structural stability, vibration resistance, and ease of access. These supports must be independent of piping loads and must maintain proper alignment and rigidity throughout all operating and environmental conditions. Mounting supports may only be attached directly to process lines with explicit approval and must not be used on pipe diameters smaller than DN100, on insulated lines, or in vibrating surfaces. If clamped to dissimilar metals, insulating materials must be introduced to prevent electrolytic corrosion. Supports must not be affixed to grating surfaces, as these do not offer sufficient mechanical stiffness and obstruct maintenance access, such as painting or lifting. In fireproofed environments, instrument supports must be welded to the steel structure prior to application of fireproofing materials. All designs must ensure that access, labeling, and future servicing are unobstructed. Standardized mounting plates. Modular integration for heating protection and identification. Each instrument and its manifold must be installed on a standardized mounting plate that accommodates not just the device, but also optional accessories like heating blocks, terminal enclosures, insulation covers, protective shades, and nameplates. These mounting plates allow for repeatable, field-proven configurations and ensure consistent installation quality across projects. Mounting plates must support tool-free removal and reinstallation of accessories during maintenance, with all identification complying with corporate standards. Dedicated drawings such as S37.815 and S37.816 provide templates for installations with or without protective shades. Impulse line routing. Controlled geometry for signal integrity and structural protection. Impulse tubing must be routed to minimize length, avoid horizontal runs, and limit the number of joints. Tubing should slope at a minimum ratio of 1:5 to allow trapped gases or condensates to return safely to the process or the instrument, depending on service type. Straight tubing runs up to 1 meter may be self-supporting. Longer lengths must be clamped at 1 meter intervals. Spacers must be used between tubing and supports to eliminate galvanic corrosion. Where multiple lines are routed together, they should be bundled closely to minimize footprint and facilitate coordinated insulation. Heavy components, such as seal pots, must be independently supported to avoid transferring stress to compression fittings or tubing. Thermal expansion loops must be included where temperature cycling is significant, and impulse lines must be flexible enough to absorb vibration from connected equipment. Dynamic protection, design against thermal and mechanical disturbance. Installations in steam, cryogenic, or vibration-prone environments must incorporate flexible geometries, such as expansion loops or offset bends, to prevent fatigue and maintain seal integrity. Lines must never be stretched tight or constrained in a manner that transmits process movement directly to fittings or instrument bodies. Impulse lines should never incorporate flexible hoses or bellows-type elements to compensate for movement. These introduce complexity, higher failure risk, and are not consistent with standardized design practice. Instrument-to-manifold connections, standardized interfaces for consistency and safety. Connections between differential pressure instruments and their manifolds must use proven, standardized interfaces to ensure sealing integrity and serviceability. Where available, connections must conform to IEC 61508 Type A dimensions with O-rings specified per ISO 36011. This includes extended spigot designs for compatibility with a wide range of transmitters. Where non-standard connections are used, such as coplanar configurations, vendor-specific mounting kits must be applied, and the full assembly must be reviewed for compliance with operating pressure, temperature, and sealing performance. Conclusion: structural discipline for safe, reliable, and maintainable measurement. Mounting remote instruments is not a secondary concern. It is a structural and reliability critical element of the entire measurement system. Every support, plate, and tubing route must reflect engineered discipline, ensuring protection against vibration, thermal cycling, and mechanical misalignment. Standardized mounting assemblies, careful routing practices, and certified connection interfaces together form the backbone of a resilient, low-maintenance remote instrument installation. Filling, flushing, venting, and draining, engineered access for safe maintenance and process integrity, controlled access for fluid handling and isolation. Impulse line designs must incorporate dedicated provisions for filling, flushing, venting, and draining to support safe maintenance and to ensure measurement reliability in the presence of aggressive, toxic, or high-viscosity fluids. These provisions must allow controlled handling of both process and seal fluids without exposure risk to personnel or the environment. Where the removal or replacement of seal or process fluid poses a hazard or contamination risk, flushing and neutralizing must be possible before any disconnection occurs. The impulse line system should include connections compatible with mobile pump or refill units, allowing for closed-loop fluid management without venting to the atmosphere. Drain and vent control, tamper resistance, and spill mitigation. Vent and drain valves must be tamper-resistant and designed to prevent accidental or unauthorized operation. Each connection must include a downward-facing stub of tubing, typically 500 millimeters in length, to direct any released fluid safely downward, avoiding contact with personnel or critical equipment. Direct discharge to atmosphere is discouraged. Instead, wherever possible, fluids should be captured and returned to the process system or safely collected via designated containment vessels. Open drains and atmospheric vents are increasingly phased out in favor of enclosed systems due to their vulnerability, environmental impact, and high lifecycle cost. Flushing and seal fluid replenishment, safe injection and recovery. Filling and flushing connections must be included for any system where the process or seal fluid is hazardous or corrosive. Seal fluids require periodic replacement. Flushing is needed to remove deposits or neutralize reactive materials. These connectors must be fitted with check valves and capped compression ends to prevent backflow and maintain containment integrity. When not in use, connections must be sealed with plug caps secured via chain or similar means to prevent loss and contamination. Reducing fixed drain and vent infrastructure, favoring mobile systems. Fixed piping to flare or drain systems is discouraged due to cost, complexity, and susceptibility to fouling. Instead, impulse lines should be designed to interface easily with portable, purpose-built service units that can safely manage seal liquid removal, replenishment, or neutralization. These units reduce the number of permanent penetrations into containment systems and enhance operational flexibility during commissioning or shutdowns. Conclusion: designed openings, not weak points. Flushing, venting, and draining are essential aspects of impulse line integrity, not merely maintenance conveniences. Each connection must serve a clear purpose, be resistant to tampering, and eliminate environmental or personnel exposure risks. By prioritizing mobile solutions, self-contained flushing circuits, and intelligent isolation techniques, the system maintains operational safety while reducing long-term maintenance burdens and regulatory concerns.